Welcome back everyone to Data Science for Everyone. Today we're going to be talking about linear regression. So basically I'm going to go through this as an example, okay? So we're going to be using a pretty common data set, and it's the US housing prices data set. Now the goal of this is pretend that you're a real estate agent, or maybe you're working for a real estate company, and you want to create a model that allows you to put in a few information or some features about a house, and it's going to return back an estimate about how well the price will sell, or at what price it may sell at, or how it will sell, good or bad. The data set we're going to use is going to create something like the area average income, the average area of the house age, the number of rooms, number of bedrooms, the area population, the price, and also the address. But we're probably going to go on and drop the address after we probably take a quick look at the data. And so we're going to go through this as a full example. And if we have time, I may also go through and we may redo another one utilizing a similar data set. Or I may save that for you guys to do as homework for today. Actually, I may do that actually. So first off, let's get in our data. Now first we're going to be using this curl. We're going to be grabbing the housing data set. Now, then let's have our standard imports. So let's do import pandas as PD, import numpy as MP, import seaborn as SNS. And then import matplotlib.pyplot as PLT, and then we'll also make sure that we do matplotlib inline. So first off, let's go about also importing the data. So again, all of this should be review for you guys that have done stuff with data management and pandas and etc. So, but just again, this part of this is just going to be a bit of a review on how to do some exploratory data analysis. So let's call this data housing, and we'll do pd.read CSV, and then we will grab the housing.csv data. So, and that's what I saved it in here using curl. So first off, let's look at the housing.head. And again, we see here that everything looks to be in relative order, but let's double check that everything is in the proper format. So let's do housing.info. We see here that everything is a float besides the address. So for the ease of doing the linear regression and not having to do any conversion methods, we'll drop this address here in just a second. Now let's also go through and maybe look at the descriptive statistics. Housing.describe. And so we see here that we have full data on everything. The price is going to be our variable of interest here. And so everything else will wind up being a feature. Let's see what else we can do here. Let's also just make sure, and we'll go in and we'll grab our column names. So we can take a look at them. I would personally like to clean up all of the column names. So we can do this by just using a little bit of Python magic here. So let's take a look. So let's say x.stir, let's do dot lower, and let's see for x in housing. Let's see how this looks. All right, we also want to dot replace periods with nothing. Let's see how that looks. That looks good. And then we want to, let's say we also want to replace spaces with underscores. Let's see how that looks. All right, that will look good. So then now let's take this and use the housing.columns is going to be equal to that list. Let's run that. Whoops, misspelled housing. So let's change this to housing. And just a reminder, this here, it'll be okay. So let me double check that actually went through. Housing doc. Did that actually go through? Oh, whoops. It's because I did column. Let's do columns. There we go. All right, now rerun that and double check. Okay, so just a reminder that this was used. We used list comprehension, okay, in order to do this, and then we did just some basic text cleaning here by lowering everything, removing periods, and exchanging the spaces for underscores so that we have this nice clean looking column headers. So next let's actually go through and do some of the EDA. First off, let's do a pair plot on all of the data. And let's take a look at what we actually have here. And again, this may take a little bit of time, so just be patient for it to run. All right, so now let's actually look at what's going on here. Now we see that everything looks pretty, we call this a shotgun blast, okay? So it's nice and doesn't have much of anything in here, but we do see that average area income and price, there is a positive correlation here. And so also the same thing with our average house age. There's a little bit of a positive correlation. Notice it's kind of squished in here, thinner on the sides, longer in there as well. We also see that it's basically similar to almost all of the other variables, at least if we look in this side here. We also see that number of bedrooms here, they are definitely, it's more of a categorical, okay, in those terms. But overall, again, we see everything has a relatively positive impact and all the data looks relatively clean. So we don't really need to clean up too much of what's going on. But since our variable of interest is price here, we can see that this is a good normal distribution, but we may want to take just a little bit of a closer look. So let's try a dist plot on our housing data. And so let's do housing price. Let's run that to take a look. And again, we see here that there is, what are they going to be using? They want to use dist plot. So let's give that a try so I can have this a little bit updated for you guys. So we can use the dist plot to see that, again, this is a very normal distribution. So that's good. Again, for fake data, that's usually what we would be expecting. There's not much different with what we see here as well. The next thing we need to do is maybe check the correlations between our data. So let's take a look at this maybe with a heat map. And so we'll do housing.core for the correlation. I think that'll do. Okay, so here we see these lighter values have higher correlation, lower values have less correlation. So items that have high corollary values are our average area of income with price, and that kind of goes down from there. The house age seems to have also a positive correlation. The number of rooms also have a positive correlation, but there seems to be less when it comes to the number of bedrooms itself. Now, I would suspect also, though, that if we see here the number of rooms and the number of bedrooms are also highly correlated. And again, you would expect if there's more bedrooms, then there's going to be more rooms in general. So now let's go on to talking about, whoops, let me actually move this down. There we go. So let's talk about actually working with our model a little bit. Now we want to split our data into two, okay? So specifically we want an X and a Y. Now I like to keep them as this proper X. A large X is going to be our feature matrix. And so what we actually want is we want all of our variables, okay, but we do not want, we would want to drop, well, you know what, let me do Y first, so this is going to be easier. So Y is we actually want housing, and we want the price variable, okay? Now our X, we're going to grab probably, let's see, what did we have here? Let me go one up so we can actually see these. Oops. Housing.columns. And we see here we have income, housing age, number of rooms, number of bedrooms, area population. So I think we want everything except we don't want price because it is our variable of interest, and we also want to drop address. So you can go and we could just copy all of these if we want to and do something like this, housing, and then actually just put in a list of all of them in there. Or if you want to, we can do something, and let me just show you what it looks like. Is if we do housing.drop, and so here we want to drop price and we want to drop address. Okay, and then we need to make sure that this is on the axis is equal to 1. So if we run that notice here, then it would actually make a copy of our data set, and it would give us everything except for the things that we don't want. So we will actually cut this, delete this, and we will put this in right here. So then we would have all of everything we want. I think that this, instead of just copying and pasting and everything, leaves everything a little bit better. And it just shows me, for example, I want price, but I want everything except these two. And so this gives us our X and our Y. Now the next thing we want to do is do a train test split. So we need to import from sklearn, learn.model selection, import, and we're going to do train test split. Now, when we run this, we are able to look at our train test split help. Now, if we look inside this, we can see that there's an example here. What it actually wants is that it wants us to have a couple parameters. It wants the arrays. It wants a test size, training size as well. Now it usually sets the test size to, for example, like to be 2.5, and it's everything between 0 and 1. I will usually pick something like 30 to 40%, and then we also need to pick here, for example, a random state. Now the random state allows it so that if there's any noise or anything, we can make sure that when I run the regression and you run the regression, it's going to be exactly the same every single time. So we need to always remember to set the seed. Now, there are a couple different ways to do this. You can, a lot of people have a tendency just to go through and just copy this example that they have here, and that does save us a little bit of time. In some of my other environments, I have a tendency to keep this as a hotkey so that I can just import it really quickly. So what this does, this train test split, and here I'm just grabbing all of their standards. So we're going to keep a third for the test size. We're going to have our random state equal to 42, and we're going to have split this into X train, X test, Y train, Y test. So then we have our testing and training sets split up. And when we run this, we will have our data. And so let's take a look at maybe our X train here so you can see this. And again, it looks just fine, okay? And if you notice though, the size here, it actually kind of shuffled everything and it grabbed different columns whenever it did its split. It does a very nice job. Some people, depending on the type of data that you have, there are other ways to do train test split. There's train shuffle splits. And then there's also different ways for us to utilize other tools at our disposal, particularly when we have a lot of categorical data. But since we don't have a lot of that here, and I just want to keep this as simple as possible, we will do that. So now let's go through and actually create and train the model. So creating the model, we need to grab out here from sklearn dot linear model, import, and then we want linear regression. So now we need to instantiate the model. So I'm just going to call this LM for linear model. We're going to have a linear regression, and there are, if we look inside here, there are several instances we can fit. We can fit intercept, we can normalize, we can make copies, we can change the number of jobs. But for right now, we're going to keep with our standard toolkit, and we'll talk more about maybe some hyperparameter tuning whenever we talk about more advanced models. So we run this to instantiate the model, and then we do lm.fit, and then we do x train, y train. Now notice, make sure that you are doing this on both of the training sets, okay? Because we do not want to run this on our test sets, or it will invalidate our results. And you will see here that it just kind of picked everything, all of its standards. So it's copy x is true, it fits the intercept is true, in jobs is going to be none, normalize is going to be none. So again, later on when we start having different models in this series, we'll be talking about this in terms of maybe we'll need to normalize the data that we actually use. The next thing that we're going to look at is the model evaluation. So we need to check to see how our coefficients are, what they look like, and then also how we can interpret the results. So the first thing that we want to look at is on the LM is the coefficients. Well, first maybe let's look at the intercept. So the intercept is negative 2,000, or well, 2 million. 2,600,000. We're not as interested in that right now because it's much more useful for us to be able to interpret the other coefficients. So let's create a data frame so that it actually looks nice. Because if we just look at the coefficients, so let me do lm dot coef for our coefficients, and I run this. Notice here, this doesn't actually help us any, and it doesn't look very clean. So we can actually we can clean this up by creating a data frame. So coef data frame, we'll do pd dot data frame lm dot coef, and then we also want our x dot columns, and then we want to create our columns is equal to, and we want to call this we'll call it coefficient. So now, let me add this to the bottom here so we can actually see it when we run this. So now that we see here, our coefficients for all of our variables are relatively easy for us to see. So let's go about interpreting these results. Now later on, I may show you guys how to make a function so we can take in this this coefficient data frame, and it'll actually write this out for you. But for now, let's actually have this as a nice clean slate. Now we can write this in a couple different ways. So usually we write ceteris paribus, but this is equivalent to holding all other features fixed. Okay, so ceteris paribus is actually holding all things the same. If it's in a perfect world and our regression here is the only world that actually matters, there's no other extenuating circumstances, there's no other data except for what we have here, that will allow us to hold this ceteris paribus. So I will usually just say something like CP. And again, when you're writing this out, I would usually write out holding all other things fixed or all other features fixed, but I'll just write CP in order to keep this a little bit more simple. So CP, a 1 unit increase in, and here we're going to say average area income is associated with an increase of, and then let me put something, some string in here. Let's see. So the average area income here is 21.50. Let's say 21.59. So $21.59. And so what this means is, all other things being equal, a 1 unit increase in the average area income comes with an increase of $59 increase in the housing price. And so maybe this is the housing price per square foot. I don't know. So then the same thing then is, same thing with the age, same thing with all of these others. So we can go through and actually do this relatively quickly. I'm just going to copy this, paste it. And so if a 1 unit increase in the average, and let's change this to house age, is associated with an increase of that number. Okay, so again, what we see here, all of these numbers, just let me say this, okay? I'm copying and pasting this increase in here, and that's because all of these numbers are positive. If there is a negative sign, then that is a decrease in the in the value of that area. And again, we haven't talked about the error rate here either, but we'll talk about that probably at a later date. But this is just the basics of running our linear regression model. And let me go on and finish doing each of these, and then we'll stop for a bit. So let's do, whoops, I want this whole thing. And we need this for how many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we have this one. We have average number of rooms. Average number of rooms here. This big thing here goes here. This one will go right there. This one will go right here. And then this last one right here. So we see now that it's actually relatively easy to write a linear regression function. And this does actually a decent job on predicting housing prices itself. But again, we can probably do a little bit better. We haven't actually run any of our scoring metrics or anything else, but we're going to leave that probably for a, you know what, maybe we do need to do this. So maybe, all right, we'll actually run the metrics probably in a later date with another example. So the next step in this, okay, would be to actually run and do some predictions. So if we want to grab actual predictions, let's call this predictions, is equal to our linear model, predict, and then we would use our X test to run our predictions. So if I do something like plt.scatter y test and our predictions, and I run this, we actually see, oh, this actually does pretty good. Now, the way that we can kind of visualize this is if we drew a 45-degree line in here, the closer all of these predictions are to that 45-degree line from end to end would actually indicate a better fit. So this one it's a little fat. Now, we're not saying that it's great, we're not saying that it's perfect, but it actually looks relatively decent. And so that's where we're using our predictions. So these are our y hat values, and this is our actual y value. So this is what we're testing. We predicted these, we got these. And so this is a great way to do a visualization. If, for example, you see them and they're scattered out all over the place, then you're going to be having a little bit of an issue. So let's also then look at, instead of doing a scatter plot, let's look at a residual plot. So we'll do sns.displot, and we want y test minus our predictions. And then we want to look at the bins. We're going to set this maybe to 50 for now. And run this. And we see here that the predictions are relatively uniform. The residuals are relatively uniform. That's good. And what this is actually looking at is the kind of looking at the error that we have here. And if this is skewed off in one direction or another, this is going to tell you that you need to probably do a little bit of normalization to your data, or you need to look and see if you are wanting to change up your variables. But this is a very good indicator to tell you how well you're doing. Both of these plots are. Now, finally, one of the last things that we need to look at is how we go about. Let me put in some more notes here. Is looking and doing our evaluation metrics. Now we have, for linear regression, we have 3 common types of these. This is mean absolute error, and that's this first one here. We have our mean squared error, okay, and that's this one here, and then we have our root mean squared error, which is here. Now, the MAE is going to definitely be the easiest to understand because it's an average error. Now, probably the MSE is probably one of the most popular because the MSE actually punishes these larger errors, and they also tend to be useful in the real world. Now, the RMSE is by far the most popular, and that's because the RMSE is interpretable in Y units. So, for example, here we're talking about this, our predictions in terms of dollars. Well, it would tell you how much error you have in terms of dollar values. So let's go through and actually run this out. So from sklearn.metrics import. Oh, actually, you know what? Let's just do this. Let's do from sklearn import metrics instead of grabbing them all out each time. And let's write up a bit of a template here. So let's do print. You know what? We won't even do that. We'll just do MAE, comma, metrics, dot, mean, absolute error. And then we want this y test, not yeast, y test, and then our predictions. And then we're going to do print. We want our MSE here, and we want our metrics, and then we want mean, and then here we want our squared error, and again we want our y test, and then our predictions. Add another one there, and then we'll do a print, and we also want our RMSE, and we want here. Let's do a square root. So MP square root, and then we actually want this whole thing here. put that inside there. And so when we run this, we actually see here that our we're looking at our relative accuracy score. So you can say that that we've actually finished our first full example for a linear regression model, and we can see here that we can be correct in our model by plus or minus probably $100,000 given our accuracy of our model, which may not be great. I wouldn't say that that's probably the best. So that means that we could probably add in more variables and help with cleaning up this root mean squared error to be able to see what maybe we can do a little bit better. So, all right, and that's going to do it for today. I hope you guys enjoyed this video. If you liked it, please comment and subscribe down below and give us a thumbs up, and I'll see you next time. Bye-bye.